about the science stuff. Professor Ken Rangel explains. And I'm going to be doing my video project on entropy. So entropy is how energy is dispersed throughout a system, but more specifically, how many modes that energy can be stored in that system. And in physical chemistry, the system is molecules and modes is phase changes. And moving on, that makes more sense when we describe the three main contributors to entropy, which is size, phase, and temperature. The bigger the size, the more movement and more likely it is to interact with its environment, which causes the entropy to go up. For example, and then moving on to phase, if it's in a gas state, it has more movement, more flow to its surroundings, causing more interactions. While if it's a solid, it's more rigid, compact, preventing that movement and interactions from occurring. And then lastly, temperature. Temperature directly affects entropy, which is why when we get to the equation to find entropy between two different temperatures, when we focus on the standard entropy or the constant, we can see that for the standard conditions, it has to be conducted at 0 Kelvin and 1 atmosphere, as opposed to what we regularly work with, which is 298 Kelvin and 1 atmosphere. Also, another factor about standard entropy is that it's absolute, because it starts from 0 and then it gets to whatever value it does, rather than doing the difference, which is final minus initial. And this starting at 0 is because we use the second law of thermodynamics to assume that it is a crystalline solid without any entropy. And for heat capacity, basically that's saying that every molecule has its own heat capacity individualistic to that molecule. For the equation, now we move on to the integral part, which is basically heat capacity in relationship to temperature. And as you can see right now, we're using a 6th polynomial of the equation of heat capacity in relation to temperature. And then from there, we divide that by temperature, because we're accounting for temperature twice if we use that original equation. And then lastly, when we take the integral of that, that allows us to get our change of entropy at that over the range of temperature 1 to temperature 2. And that is that equation. And then moving on to exceptions, this does not work when there is 2 phase changes in a system, because as we learned before, heat capacity changes with phase change, because the amount of heat required to heat up a molecule further increases as temperature goes up. So that's why we change the equation to the enthalpy divided by the temperature, and that's going to give us our entropy for the phase change. But in those systems, we also have to account for the entropy of the temperature. So there's going to be 2 entropies if there's 2 phase changes in that system. Lastly, this kind of like wraps that up, and we're going to move on to what I've learned over this course. I've gotten very good at Excel. Cause and effect, there's a lot of relationships that we observed using graphs and inverse graphs. And lastly, problems, moving on to problem solving. Excel's not always kind, which leads you to kind of have to come up with solutions quickly. And lastly, vapor pressure is very scary. When we did that assignment, I did not know it impacts greenhouse gases by that much. And that is my time. Woo! I just want to make sure it's under 3 minutes. Let's go.